Oh, that's... wow. Okay. No, that's wrong. Oh. Wow. Interesting. It's root. Nope. What? Oh. Oh, yeah, oh, that's also wrong. Oh. Oh. How did that not? That's pretty funny. But I'm just, yeah, I shouldn't do this, right? I should just do the following. Okay. Looks like slowly decreasing. Maybe going the right direction. Okay, so we're gonna try this. We need to. So large. What? Oh, this syntax. It's kind of slow. I mean, I don't know if this is, well, we'll see. It might, it should be, we'll all right. That's what it is. I can quickly explain what happened. I mean, yeah, we did some very simple eval hacks. I had to hack around. So basically, we just loop over these expressions a very large number of times. This is the very lazy and like it's slow. It's quadratic. Like there are like you could do like a topological sort and stuff on dependencies or something fancier like that if you want to quickly figure out just run the right expressions in the right order. But as I was very lazy and didn't want to think about that stuff, I have this very simple quadratic scan thing where we just iterate over each thing, and then whenever we see something that we know how to evaluate, we evaluate it. And eventually, by scanning the whole thing enough times, you collect all the dependencies, and you are able to evaluate root. So that was enough for the first part. For the second part, it's a bit more interesting. A more sort of elaborate or correct way to solve this problem, I would imagine, is you build some kind of polynomial expression. Like you keep track, like you can tell by inspection from these like that, because they're actually, I guess these are rational. It might be a bit annoying, but you can tell, like, because they're only 4 basic arithmetic operations going on, you know that every single one of these variables will be a rational function. That is a polynomial divided by a polynomial function of the input UMN. So one thing you could do is build a rational class that sort of encapsulates that, and that you can perform these basic arithmetic operations on, and then at the end you can calculate, like, precisely that root has comparing two things that are both rational functions of UMN, and that way you can, like, solve it exactly. Unfortunately, that's quite difficult, so we're doing a sort of brute forcey technique, making assumption that, you know, this rational function will be probably be monotonic on integers near the range that we care about, which is not obvious. Like, this is like stab in the dark, but it would be like pretty, like, it would have to be pretty much engineered to be that way, because like most rational functions are monotonic for most of their domain, and numbers that we already saw were quite large, so it seems like a reasonable assumption. And here we keep the same correct loop, which made our code somewhat slow. But what we can do is each time we just pick a value for UMN, see what root gives us, and binary search on that. So I seeded this binary search by sort of manual inspection, running a few iterations of the program myself to verify that, you know, there's some number where the left side is larger than the right side, and a much larger number where the left side is smaller than the right side. And so, assuming that the rational function formed by the subtraction of the two rational functions that feed into roots eventually, assuming that that is monotonic, we binary search on it to find the hopefully unique value of UMN that makes them equal. That is, makes their difference equal to 0. So you just check whether this thing is positive or negative, and yeah, you have your solution in log of these numbers, so that's not too slow. This thing, I think, did, like, slow me down a bit, just the fact that this is so quadratic is so inefficient. There are clearly other optimizations I could have done here. Let me think about this. I'm actually evaluating this every single time I run through. Like, even if I encountered something already and I already know what the value is, I'm like grabbing the operation again and running it. Also, I guess, like, the most interesting newlist specific component of this is the eval hack I had to end up using. The problem, if you look at the design docs that may or may not exist, if you look at the README, you should know that, like, newlist does not handle unary minus very well. Like, in Python, you can write like -3 times -3, and Python knows what it is. In Nulith, you cannot do that. Because this parses as like these 3 things, like these 5 things, like all in a row, and it sort of looks like 3 is the operator between minus and star. It just doesn't make sense. So you have to write this or this. And what I did not realize until this moment is that Nulith has fractions. Like this is an exact fraction. But it does a simplification. It is, 2 big ints. But I did not realize until today that like if you have a negative fraction and you format it as a string, this cannot be valid. That's the for sort of the same reason it runs the same problem. So we eval only the operator. And this is a function in Nulith, which we call, like with the 2 numbers we have seen calculated from previous iterations or directly from past loops, or even that the problem directly provided to us. Yeah, otherwise, it's, I guess, pretty standard stuff. I expect most solutions we think how confident I am in this. There are many ways to figure out how to run these expressions in the order, but I expect that a lot of people will reach for some eval-like thing to figure out what operation to run. I have blathered on for long enough, I think.